Alright, so we are continuing our march through the detailed specification of picoscopes, and we are at the meat and potatoes of any scope, the sampling rate. Let's be clear that picoscopes sample in two ways. One is block mode and one is streaming mode. In the block mode, the picoscope starts sampling and fills in the buffer, whatever the size of the buffer is, and only then sends the data to the PC. Then the process starts over again. What it means is that you can sample at very high rate, but then there will be a gap while the picoscope is sending the data to the PC. However, there is a streaming mode in which the picoscope is sending the data to the PC at the same time as it is sampling. Of course, that means that the sampling rate would be lower. Let's start with the sampling rate for the block mode for automotive picoscopes. The numbers are quite impressive. For one channel, they can be up to 400 megasamples per second. For two channels, up to 200. And for the 4-channel scope, with 3 or 4 channels in use, up to 100 megasamples per second. That will cover pretty much all the signals you can get in the automotive world except for the car Ethernet. Let's see how this compares to Picoscope 2000 series. On the baby Pico, we get up to 100 megasamples per second. 25 megahertz Picoscope achieves 200 megasamples per second and up. This is on one channel. If you're using two channels, then obviously the numbers will be split in half. Notice that Picoscope 2000 series also have something called equivalent sampling rate, ETS mode, with ridiculously high reported numbers. This is something that can be used only for special repetitive signals, and so far I have no examples how this can be used for automotive signals, so we are going to skip discussion of these ones for now. At such high sampling rates, the usefulness of the capture may be limited by the buffer memory, and indeed, for 10 and 25 MHz oscilloscopes, this number is measured in kilosamples, while for 50 MHz and up, this is measured in megasamples. And these numbers can be very useful when, for example, you are looking at the data transmission. The large buffer allows you to capture many packets, and then you can do serial decoding on those and maybe find something unusual. With a smaller buffer, you might be able to capture only a few packets, or even sometimes only half a packet. And so while you can look at the signal, maybe confirm that the transitions are good, that the integrity of the line is okay, you might not be able to do serial decoding with those. Now, the highest number we've seen for the Picoscope 2000 series is 128 megasamples in the buffer. Now, let's take a look at the automotive Picoscope and see that the number is 250 megasamples. So it definitely blows out of the water the capabilities of the Pico 2000 series. You can really try to capture many packets at very high sampling rates. However, with automotive picoscopes, you often will not even need the buffer memory, as you might just use the USB streaming for pulling in the data, because even with USB 2.0, the maximum sampling rate achievable is 10 megasamples per second, and it goes up to 20 megasamples per second if your PC has USB 3.0 and supports such transfer speeds. Even if you use several channels with 20 megasamples per second divided among all the channels, you will still get crystal clear waveforms for CAN bus signal, for example. So you can just enable USB streaming and collect that data until the Picoscope software runs out of its waveform buffer, which is limited to 10,000 waveforms or the memory of your PC. How does this compare to USB streaming with the Pico 2000 series? Well, let's take a look. The baby Pico is capable of streaming at 1 megasamples per second, and this is with both channels enabled. I checked that empirically, and there is a video on this channel that shows how to enable streaming on this oscilloscope and what to expect. The faster oscilloscopes are capable of streaming up to 9.6 megasamples per second. Of course, this is shared between the channels. There are conflicting reports about 2405A oscilloscope. Here it's listed as streaming at 1 megasamples per second, but one of the viewers, John Byrne, has reported that he was able to get 8 megasamples per second. So these numbers require further testing and verification. Now let's try to answer the following question. So the baby Pico is capable of streaming at 1 megasamples per second. Does it mean that we can stream waveforms for, let's say, CAN bus signal? And my answer to that is, well, not quite, but it might work for you. CAN bus signal is 500 kilobit per second. So the sampling rate is just 2 times the data rate. This is not enough to have a detailed view of the waveform and not enough to do the serial decoding. However, you will still see the transitions, and you will be able to confirm the maximum and the minimum voltages on each line, see that the signals mirror each other, and so that might be enough for your diagnosis. Of course, this problem is not an issue for faster oscilloscopes, so for those that can sample at 9.6 megasamples per second, or for the automotive oscilloscopes which can sample even faster with USB 3.0. By the way, when you're sampling that fast, make sure that your PC is able to accept such a signal. That often means that you need to make sure that the USB port is dedicated to the Picoscope, and you cannot have anything else that will slow it down. So no USB hubs, and try not to connect other devices that use USB port extensively. One thing to note, it can sometimes be confusing whether your Picoscope is in the block mode or the USB streaming mode. And actually there are preferences where you can set when you want one mode or the other mode. So please look up the help in Picoscope on that. Sometimes it's helpful to have a properties dialog open in the Picoscope so that you can see what the sampling rate is. Time-based ranges parameter tells you how much time you can have across the screen. At the lowest setting, you can have 1 microsecond across the screen, which corresponds to 100 nanoseconds per division. And on the upper range, you can have up to 14 hours across the screen, which will correspond to 5,000 seconds per division, pretty much using your Picoscope as a graphing meter. But at such time bases, make sure that you have the proper sampling rate set up. So you really want to enable the properties dialog in your Picoscope software and pay attention to the sampling rate that the Picoscope is using. Okay, now we are ready to talk about the dynamic performance, which is how accurate your oscilloscope is. The first parameter is crosstalk between channels, and you probably know what it is. It happens when you have, let's say, 2 channels enabled, and one of them is receiving an ignition waveform, and the other channel is doing something else, but nevertheless on that channel you see a faint ghost of the ignition waveform that you also have on the first channel. And there could be two reasons for that. One is that it's actually the ignition waveform imprinting itself on the signal that you are measuring, because all the wiring is pretty much like antennas. But there could be a second reason, that inside the oscilloscope itself there is an interference from one channel to another, and that's why you see this signal. And the automotive picoscopes guarantee that the ratio between the waveform that's received on one channel and how it interferes on the other is 4000 to 1. All you need to know that it's a pretty awesome value. Compare that to Picoscope 2000 series, where we also have this parameter, and it's only guaranteed to be better than 201 or 301 for higher-end oscilloscopes. So, well, basically 4000 is awesome. Harmonic distortion is a specific type of distortion where you're measuring, let's say, a sine wave, but on the waveform you also see other sine waves with the frequencies that are several times higher than the original sine wave. And this parameter is measured as a ratio of the ghost sine waves to the original one. And as electrical engineers like to do, they always measure things in decibels. So it says minus 60 decibels. All you need to know, it's a pretty awesome value. And for Picoscope 2000 series, this is only guaranteed to be minus 50 decibel. Spurious free dynamic range. It's a horrible combination of words. What does it mean? Well, if you've ever done frequency plots on Picoscope, you would know that if you feed a sine wave into it, you will see a big peak at that particular frequency. However, even if you feed it with ideal sine wave, there will also be some small peaks at other frequencies, basically an oscilloscope added noise. And the SFDR is measuring the ratio between that big peak from the original sine wave and the maximum peaks from those spurious noise. And it's also expressed in decibels, and this is a pretty good number. We can compare it to Pico 2000 series, where it's listed at 52 decibel. So automotive oscilloscope wins again. However, if we talk about the noise itself expressed as RMS, it's 220 microvolts on a 50 millivolt range, and surprisingly for Pico 2000 series, the baby Pico achieves 150 microvolts on the same range. So it looks like Pico 2000 series is adding less noise than the automotive Picoscope. Surprising, but that's how it is. Bandit flatness. If you feed the sine wave of a certain amplitude and frequency into the oscilloscope, we are going to see a sine wave, but with a slightly different amplitude. If the frequency is low or DC voltage, then we are going to see an amplitude slightly higher. And if we feed it in with a full bandwidth sine wave, and remember that for this oscilloscope it's 20 megahertz, we are going to see a sharply lower amplitude, minus 3 decibel, which is, in engineering talk, just 70% of the voltage. For Pico 2000 series, we see very similar numbers, so there are no surprises there. Moving on, the ADC ENOB. ADC stands for analog to digital converter, and ENOB is effective number of bits. You see, Every oscilloscope has an input circuitry, and then the signal is fed into the ADC. That ADC is not ideal. Mathematicians came up with a model for an ideal analog to digital converter with n number of bits, where n doesn't even have to be integer. The usefulness of that, we can compare an ideal model to the real ADC. And the real ADC is listed as 12 bits, but it delivers the same precision as a 10.8 ideal model ADC. So this number that we have, 10.8, is approximately 1 bit less than the 12 bits, is just an acknowledgement of that.